All right, today we're going to be looking at our second individual gas law. This one's called Boyle's law. And before we get too far into this, let's start off by establishing something that we need to keep in mind throughout this entire chapter, and that is something called kinetic molecular theory. And we'll abbreviate this KMT. It's a real simple theory that says that molecules are always in motion. And the factor that affects this motion is heat, which we usually indicate by temperature. And so we'll say the greater the heat, the faster the motion. If you are going to take AP chemistry, you'll learn to call that by another name, but we'll worry about that later. And of course, the lower the heat, the slower motion. And we're going to get into this a little bit later in another law, and we'll use a different term for measuring heat, but for right now we'll just leave it like it is. So here is a fairly good representation of what's going on with gases, and what we'll do is we'll add some gas to this chamber. Right now it is showing a temperature of 27 degrees Celsius. I don't know if you can read that. And it is showing a pressure that's hovering between 8 and 9 atmospheres. And the kinetic molecular theory shows that as we increase the heat, the speed increases, and as we decrease, the speed decreases. We'll worry about that later. What we're interested in now is the volume. And so this chamber is interesting because we can change the volume of this chamber at will. And what we're going to do is decrease the volume. And what we want to do is pay attention to what this pressure gauge is doing. So what we'll do is we'll decrease this volume slowly. And notice what's happened to our pressure gauge. It looks like we have pretty much chopped the volume in half, and it looks like the volume has doubled. Let's go back out to our original volume right here between 8 and 9 atmospheres. And now what we'll do is we'll increase the volume. And look what happens to our pressure. I'm going to let you guys think about that and why that works. And we're going to set up another experiment here and try to look at this from another point of view. This is what's known as a vacuum chamber. And it is a sealed container that we have a pressure gauge hooked up to, and it is currently reading 0.99 atmospheres, a little less than 1 atmosphere, which makes sense because we're a little higher than sea level here in Wheaton. We're at 700 feet above sea level, so a little bit less. And let's zoom in so you can see what that looks like. So a little bit less than 1 atmosphere in real time. All right. So what we're going to do is we're going to put an object in this vacuum chamber whose volume is not guaranteed to be constant, and see what happens when we start changing the pressure. Here is our object that is not a constant volume. Let's see what happens when we put this in the vacuum chamber. This balloon has a tendency to fall to the bottom, so what I have done is I've put a little Scotch tape on it so that it will stick to the side near the top. and will stay out of the way. And so here is what this looks like with our balloon stuck near the top. Now we'll hook up our vacuum pump. And I think that's the best our vacuum pump can do. So, what do you think is going on? What is the relationship between pressure and volume? As we lower the pressure in the chamber, what happens to the volume? And I'm going to open the valve at the top and resume atmospheric pressure, and you tell me, as the pressure climbs, what happens to the volume of our balloon. I think that was all it could take. So clearly, what's this relationship going on here? And let's take a closer look. And what we notice is that as the pressure decreases inside our vacuum chamber, hopefully you saw that the volume of our object, in this case our balloon, increases. This is what we call an inverse relationship, or otherwise known as an inverse proportion. And we're going to represent this mathematically with a very simple equation. P1V1 equals P2V2, where P1V1 is our initial pressure and volume, and P2V2 is our final pressure and volume. So let's set up a problem that's pretty exemplary of what it is we're trying to solve here. So here's the type of question you can expect me to ask. A balloon occupies a volume of 1 liter at 1 atmosphere. What will the new volume be if the pressure is reduced to 0.25 atmospheres? What I like to do, because it's easy for me to get these things mixed up, is I like to establish what I know. So my initial pressure, my P1, is 1 atmosphere. My initial volume, my V1, is 1 liter. And there's lots of different units we could use for volume: liters, cubic centimeters, milliliters, cubic meters. Don't be surprised if you see a bunch of different ones. And what we're trying to find is our new volume. So P2 is what we're looking for. We're trying to find our new volume V2 if we have a new pressure of 0.25 atmospheres. So when I do this, it just helps me keep things straight. So I'm going to plug everything into this equation. We're going to say P1, 1 atmosphere, times V1, 1 liter, is equal to P2, 0.25 atmospheres, times V2, which is what we're trying to find. So to get V2 by itself, I'm obviously going to divide both sides by 0.25 atmospheres. And that's going to eliminate it from this side. Now look what happens to our units. When we do this, we divide both sides by atmospheres, and that means that atmospheres cancels, and it leaves liters as our only unit. So what's our V2? 1 divided by 0.25 is 4 liters. As we expect, As the pressure decreases, the volume increases. All right, pretty easy. So take this for a spin, all right? And I'll see you guys on the next one.